Hello there, and welcome. Tonight we're going to explore one of the most fundamental questions in all of science. How old is the universe? Now you might think this is a settled question. After all, you've probably heard the number 13.8 billion years mentioned countless times. It's in textbooks, documentaries, and science articles everywhere. But what if I told you that this number, precise as it seems, might not be the whole story? Recent observations from some of our most powerful telescopes have revealed something unexpected. Galaxies that seem too mature, too organized, too massive to exist when they do. Stars that appear older than the universe itself. Structures that shouldn't have had time to form. These discoveries have sparked a fascinating debate in the scientific community, one that challenges what we thought we knew about the age and evolution of our cosmos. So let's dive into this mystery together. We'll explore how scientists actually measure the age of the universe, what these puzzling new observations really mean, and whether we might need to rethink one of the most basic facts about our existence. Before we can understand why the universe might be older than we think, we need to understand how scientists arrived at that 13.8 billion year figure in the first place. And trust me, the method they use is both ingenious and surprisingly straightforward once you break it down. The story begins in the 1920s with an astronomer named Edwin Hubble. Working at the Mount Wilson Observatory in California, Hubble made an observation that would completely transform our understanding of the cosmos. He discovered that galaxies weren't just sitting still in space, they were moving. And not just moving randomly, but moving away from us. Even more remarkably, the farther away a galaxy was, the faster it appeared to be receding. Think about it this way. Imagine you're standing in the middle of a crowd, and everyone around you starts walking away in different directions. If you notice that people who are farther from you are moving away faster than people who are closer, what does that tell you? It suggests that at some point in the past, everyone was in the same place. The crowd was gathered together. That's essentially what Hubble's observation implied about the universe. If galaxies are moving apart, and if we could run time backward, like rewinding a movie, we'd see them all coming together. Keep going back far enough, and everything in the universe would be compressed into an incredibly small, incredibly dense point. This realization gave birth to what we now call the Big Bang Theory. But here's where it gets interesting for our purposes. If we know how fast galaxies are moving apart, we can calculate how long it's been since they were all together. It's like seeing two cars driving away from each other on a highway. If you know their speeds, you can figure out when they must have been at the same starting point. The rate at which the universe is expanding is called the Hubble constant, named after Edwin Hubble himself. Scientists measure this by observing how quickly distant objects are moving away from us. The faster the expansion rate, the younger the universe would be, because things wouldn't have needed as much time to get as far apart as they are now. Conversely, a slower expansion rate would suggest an older universe. Now you might wonder, how do scientists actually measure these cosmic speeds and distances? The technique relies on something called redshift. When objects in space move away from us, the light they emit gets stretched out, shifting toward the red end of the spectrum. The faster something is moving away, the more its light gets redshifted. By measuring this redshift and combining it with distance measurements, scientists can calculate the expansion rate of the universe. But measuring distances in space isn't simple. You can't exactly stretch a tape measure to a distant galaxy. Instead, astronomers use what they call standard candles, objects whose true brightness they know. By comparing how bright these objects appear from Earth to how bright they actually are, scientists can calculate how far away they must be. It's the same principle as knowing that a distant streetlight looks dimmer than a nearby one, even though they're actually the same brightness. One of the most important standard candles is a type of exploding star called a Type Ia supernova. These stellar explosions have a consistent peak brightness, making them ideal cosmic measuring sticks. Another crucial tool is something called the cosmic microwave background, or CMB. This is radiation left over from when the universe was very young, just 380,000 years after the Big Bang. By studying the patterns in this ancient light, scientists can learn about the universe's composition, geometry, and expansion rate. Using all these tools together, scientists have measured the Hubble constant and worked backwards to calculate when the Big Bang must have occurred. The current widely accepted figure, as measured by the European Space Agency's Planck satellite, puts the age of the universe at 13.8 billion years, give or take about 20 million years. That's an incredibly precise number. We're talking about measuring something that happened nearly 14 billion years ago, with an uncertainty of less than 0.2%. It's a testament to how far our scientific methods have come. But as we're about to see, precision and accuracy aren't always the same thing. Just because we can measure something precisely doesn't necessarily mean we're measuring the right thing, or that we have all the pieces of the puzzle. Now here's where our story takes an intriguing turn. Remember that Hubble constant we talked about, the rate at which the universe is expanding? Well, it turns out that different methods of measuring it are giving different answers. And we're not talking about tiny, negligible differences. We're talking about discrepancies, significant enough to make scientists seriously question whether something might be wrong with our standard picture of the universe. Let me explain what I mean. When scientists measure the Hubble constant using the cosmic microwave background, that ancient light from the early universe, they get one value. But when they measure it using observations of the present-day universe, looking at things like supernovae and the distances to nearby galaxies, they get a different value. The difference might not sound huge at first, but in the world of precision cosmology, it's enormous. The Planck satellite measurements suggest the universe is expanding at about 67 kilometers per second per megaparsec. Don't worry too much about what those units mean. The important thing is the number, 67. But measurements using supernovae and other local observations give a value closer to 73 or 74. That's roughly a 9% difference, and it might not sound like much, but it's far larger than the margin of error in either measurement. Why does this matter? Because if the universe is expanding faster than we thought, based on local measurements, it would mean the universe is younger than 13.8 billion years. Things have been moving apart more quickly, so they haven't needed as much time to get where they are now. On the other hand, if the slower expansion rate from the cosmic microwave background is correct, then our current age estimate stands. Scientists call this disagreement the Hubble tension, and it's become one of the most pressing mysteries in modern cosmology. At first, researchers assumed it was just a measurement error, something in the data that hadn't been properly accounted for. But as measurements have gotten more and more precise, the tension has persisted. It hasn't gone away. If anything, it's become more pronounced. So what's going on? There are a few possibilities, and none of them are simple. One option is that there really is a measurement error somewhere, something subtle that scientists haven't caught yet. Maybe the way we're measuring distances to distant galaxies isn't as accurate as we think. Maybe there's something about supernovae we don't fully understand that's throwing off our calculations. But here's the thing. Multiple independent research teams using different methods and different telescopes are all finding similar results. It's hard to imagine they're all making the same mistake. That leads us to more exotic possibilities. Perhaps the universe doesn't expand at the same rate everywhere. Maybe the part of the universe we can observe is expanding differently than other parts. Or maybe the expansion rate has changed over time in ways we haven't accounted for in our models. Some scientists have even suggested that we might need to revise our understanding of dark energy, that mysterious force that's accelerating the expansion of the universe. Any of these scenarios would have profound implications. They would mean that our standard model of cosmology while incredibly successful, is missing something important. And if the local measurements are correct, and the universe is expanding faster than the early universe data suggests, then yes, the universe could be younger than 13.8 billion years, perhaps significantly younger. But before we get carried away, let's consider another intriguing possibility. What if both measurements are correct, but our interpretation of what they mean needs revision? What if there's something about the early universe, or the way the universe has evolved, that we're not accounting for? Could there be factors that would make the universe older than the standard model suggests, even if the local expansion rate is high? This brings us to some of the most puzzling observations made in recent years. Discoveries that have left astronomers scratching their heads and wondering if our timeline of cosmic history needs a serious overhaul. In December 2021, NASA launched what is arguably the most powerful space telescope ever built, the James Webb Space Telescope, or JWST for short. This incredible instrument was designed to peer deeper into space and further back in time than any telescope before it, and boy has it delivered. But along with spectacular images and groundbreaking science, JWST has also delivered something unexpected, a serious challenge to our understanding of how galaxies form and evolve. Within months of beginning its observations, JWST started finding galaxies in the very early universe that looked, well, wrong. Not wrong in the sense that they were impossible, but wrong in the sense that they shouldn't have been able to form so quickly after the Big Bang. These galaxies were too massive, too mature, too well organized for their age. Let me paint you a picture of what we expected to see. According to our standard model, the early universe was a much simpler place. In the first few 100 million years after the Big Bang, galaxies were supposed to be small, irregular, and messy. They were still in the process of forming, still gathering matter, still learning how to be galaxies, if you will. It should have taken billions of years for them to grow into the large, structured, spiral, and elliptical galaxies we see in the nearby universe today. But JWST has found galaxies that appear to be massive and well-formed when the universe was less than 1 billion years old. Some of these galaxies exist just 300 or 400 million years after the Big Bang. That's less than 3% of the current age of the universe. It's like finding a fully grown oak tree in a forest that was supposedly planted just last week. Now, before we go any further, I should mention that scientists are still analysing these observations. The interpretation of what these early galaxies really are, and how massive they truly are, is still being debated. Some of the initial estimates might be too high, but even accounting for uncertainties and possible revisions, the basic problem remains. These galaxies seem to have grown up too fast. How fast is too fast? Well, think about it this way. To build a galaxy, you need to gather an enormous amount of matter through gravity. Gas clouds need to collapse, stars need to form, and all of this takes time. Based on our current understanding of physics, there's a limit to how quickly this process can happen. It's like trying to cook a roast. Even if you turn the oven up as high as it will go, the heat can only penetrate the meat so fast. There's a physical limit to how quickly the inside will cook. In the early universe, matter could only fall together and form structures at a certain rate, governed by the strength of gravity and the density of matter at the time. For these massive galaxies to exist so early, either the universe needed more time than we thought, or something about our understanding of galaxy formation is incomplete. Could the universe simply be older, giving galaxies more time to form? That's one possibility, and it's part of what we're exploring in this video. If the Big Bang happened earlier than 13.8 billion years ago, these observations would make more sense. The galaxies would have had a few 100 million more years to get their act together, which might be enough to resolve the problem. But there are other possibilities too. Maybe the early universe was denser in some regions than we thought, allowing matter to collapse into galaxies more quickly. Maybe the first stars formed differently than stars do today, in ways that sped up galaxy formation. Maybe there's something about dark matter, that mysterious substance that makes up most of the matter in the universe, that we don't understand. Or maybe, and this is a fascinating thought, the process of cosmic inflation, that rapid expansion of space that happened in the first fraction of a second after the Big Bang, created conditions that allowed for faster structure formation than our current models predict. The point is, these observations are genuinely puzzling, and they're forcing scientists to question assumptions that had seemed solid for decades. And JWST hasn't just found mature galaxies too early, it's also found other surprises, supermassive black holes in the early universe that seem too big for their age, galaxy clusters, vast collections of galaxies held together by gravity that appear to have assembled earlier than expected. Each of these observations points to the same basic problem. The early universe seems to have been a much busier, more active place than our standard timeline suggests. Things happened faster, structures formed sooner, and if that's really the case, we might need to revisit not just the age of the universe, but our entire picture of how it evolved. Now, if galaxies that seem too mature for their age weren't puzzling enough, let me tell you about an even stranger problem. Scientists have actually found stars that appear to be older than the universe itself. Yes, you heard that right. Stars that, according to our best measurements, were born before the Big Bang. Obviously, that's impossible. Nothing can be older than the universe. So what's going on? The most famous example is a star with the rather uninspiring name HD 12283, but astronomers have given it a much better nickname, the Methuselah star, after the biblical figure who supposedly lived for 969 years. This ancient star is located relatively close to us in cosmic terms, only about 190 light years away. That's practically in our backyard by astronomical standards. Here's the problem. When scientists measured the age of this star using well-established techniques, they got a result of roughly 14.5 billion years. Remember, the universe is supposed to be 13.8 billion years old. That would make the Methuselah star about 700 million years older than the universe. It's like meeting someone who claims to have been born before their parents were born. The math simply doesn't work. How do scientists measure the age of a star anyway? It's not like stars have tree rings you can count. Instead, astronomers use what they know about stellar evolution. Stars burn fuel, primarily converting hydrogen into helium through nuclear fusion. As they age, their composition changes, and these changes affect their brightness, colour, and other observable properties. By carefully measuring a star's characteristics and comparing them to theoretical models of how stars evolve, scientists can estimate its age. The technique is well tested and generally reliable, especially for old stars like Methuselah. These ancient stars have very low amounts of heavy elements, which tells us they formed early in the universe's history when heavy elements were rare. They're called population 2 stars, and they're some of the oldest objects we can observe. So we have a star that multiple independent measurements suggest is older than the universe. What's the solution? Well, there are uncertainties in both age estimates. The uncertainty in the star's age is about 700 million years, and there's a small uncertainty in the universe's age too. When you account for these error bars, the two ages can technically overlap. The star could be slightly younger than the middle estimate, and the universe could be slightly older. Problem solved, right? Well, maybe, but it's cutting it awfully close. And Methuselah isn't the only ancient star out there. There are others with similarly problematic ages. Each one individually might be explained away by uncertainties, but collectively they start to look like a pattern. They suggest that either stars formed extremely quickly after the Big Bang, much faster than we thought possible, or the universe is older than 13.8 billion years. Let's explore that first option for a moment. Could stars have formed super early in cosmic history? According to our standard model, the first stars, called population 3 stars, formed somewhere between 100 and 200 million years after the Big Bang. These would have been massive, short-lived stars that burned through their fuel quickly and exploded, enriching the universe with the first heavy elements. The next generation of stars, population 2 stars like Methuselah, formed after these first stars had created some heavy elements, but they still formed very early, possibly within the first billion years. If some of these stars formed at the earliest possible time and have been burning steadily ever since, they could indeed be around 13 billion years old, just barely fitting within the universe's lifespan. But here's where it gets tricky. The uncertainties work both ways. What if our measurements of the universe's age are slightly off? What if factors we haven't fully accounted for mean the Big Bang happened earlier than we think? Even an extra 500 million years would resolve the tension with these ancient stars and give those early galaxies we talked about more time to mature. This brings up an important point about scientific uncertainty. When we say the universe is 13.8 billion years old, we're not claiming absolute perfect knowledge. That number comes with error bars and assumptions. It's based on our current understanding of physics, our measurements of the Hubble constant, and our interpretation of the cosmic microwave background. If any of those inputs are even slightly off, the output, the age of the universe, would change. And here's something else to consider. What if the universe went through phases of expansion we don't know about? What if there were periods in the early universe where expansion slowed or accelerated in unexpected ways? These possibilities, while speculative, could affect our age calculations without necessarily contradicting any of our observations. The Methuselah star and its ancient cousins are a reminder that even in well-established fields of science, there's always room for surprises. They're not proof that the universe is older than we think, but they're certainly a hint that our timeline might need some adjustment. To really understand the age controversy, we need to talk more about one of the most important tools in cosmology, the cosmic microwave background. This is often abbreviated as CMB, and it's essentially a baby picture of the universe. But unlike a photograph, it's a picture made of light itself, light that's been travelling through space for almost the entire history of the cosmos. Here's what happened. In the very early universe, everything was incredibly hot and dense. Matter and energy were mixed together in a searing plasma where atoms couldn't even form. Photons, particles of light, were constantly bouncing off charged particles in this plasma, unable to travel freely. The universe was opaque, like being inside a thick fog. But as the universe expanded, it cooled. Eventually, about 380,000 years after the Big Bang, it cooled enough for electrons and protons to combine and form the first neutral hydrogen atoms. This moment is called recombination, and it changed everything. With neutral atoms forming, photons were suddenly free to travel through space without constantly colliding with charged particles. The fog cleared, and the universe became transparent. The light that was released at that moment has been travelling through space ever since. And here's the remarkable thing, we can still see it today. As the universe expanded, this light was stretched out, shifting its wavelength from visible light to microwaves. That's the cosmic microwave background, a sea of microwave radiation filling all of space, a nearly uniform glow in every direction we look. The CMB is almost perfectly uniform, but not quite. There are tiny temperature variations, differences of only a few millionths of a degree, but these tiny ripples tell us an enormous amount. They reveal the density variations in the early universe, the seeds that would eventually grow into galaxies and galaxy clusters. They tell us about the composition of the universe, how much ordinary matter, and dark energy it contains. And crucially for our purposes, they tell us about the age and expansion rate of the universe. When scientists analyze the CMB, they're looking at patterns in these temperature variations. The size of the hot and cold spots, the way they're distributed, the polarization of the light, all of these contain information. It's like looking at ripples on a pond and figuring out where the stones were thrown and how hard. The European Space Agency's Planck satellite, which operated from 2009 to 2013, made the most precise measurements of the CMB to date. By analysing these measurements and fitting them to theoretical models, scientists determined that the universe is 13.797 billion years old, with an uncertainty of only about 20 million years. That's the source of the widely quoted 13.8 billion year figure. But here's the thing. This age is only as good as the model used to interpret the data. The model assumes certain things about how the universe has evolved, about the properties of dark energy and dark matter, about the expansion history. If any of these assumptions are wrong, the age calculation would be wrong too. This is where the interpretation gets interesting. The CMB gives us a snapshot of the universe at 380,000 years old. From that snapshot, we extrapolate backward to the Big Bang and forward to today. But extrapolation always involves assumptions. It's like trying to figure out how tall an adult will be by measuring them as a toddler. You can make a good estimate based on growth models, but unexpected factors could change the outcome. Some scientists have suggested that perhaps the early universe expanded differently than our standard models assume. Maybe there was an additional field or force that affected the expansion rate in ways we haven't accounted for. If so, the CMB data could be reinterpreted to give a different age for the universe. Others point out that the CMB tells us about the universe at a very specific time, when it was 380,000 years old. It doesn't directly tell us what happened before that, in the first fraction of a second after the Big Bang. If our understanding of that earliest period, the era of cosmic inflation, needs revision, it could affect our age calculations. There's also the question of cosmic variance. We can only observe the CMB from our particular location in the universe, our cosmic horizon. We're essentially looking at one sample of what the early universe was like. If our observable universe isn't perfectly representative of the universe as a whole, that could introduce biases into our measurements. None of this is to say that the CMB measurements are wrong. They're incredibly precise and have been confirmed by multiple satellites and ground-based experiments. But precision isn't the same as accuracy. You can measure something very precisely and still be measuring the wrong thing or interpreting it incorrectly. The cosmic microwave background is one of the pillars of modern cosmology, and it's given us tremendous insights into the universe's history. But like any scientific tool, it has its limitations, and its interpretation depends on the theoretical framework we use. As we encounter observations that don't quite fit, like those mature early galaxies and ancient stars, it's worth asking whether our framework needs adjustment. Now we need to talk about two of the most mysterious components of the universe, dark matter and dark energy. These aren't just footnotes in the story of cosmic age. They're major players, making up about 95% of everything that exists, and our understanding of them, or rather, our lack of complete understanding, could be key to resolving the age puzzle. Let's start with dark matter. This is matter that we can't see, but we know it's there because of its gravitational effects. Galaxies rotate in ways that don't make sense unless there's much more matter in them than we can see. Galaxy clusters hold together despite not having enough visible matter to explain their gravitational binding. And the way light from distant objects is bent as it passes by massive structures tells us there's invisible matter doing the bending. Scientists estimate that dark matter makes up about 27% of the universe. We don't know what it's made of. The leading candidates are exotic particles that barely interact with ordinary matter, which is why we can't see or detect them directly. But despite not knowing its exact nature, we can measure its effects and include them in our models of how the universe evolves. Here's why dark matter matters for the age question. Dark matter affects how structures form in the universe. More dark matter means stronger gravity, which means matter clumps together faster. If our estimates of how much dark matter exists or how it behaves are even slightly off, it could affect how quickly galaxies form. Maybe those surprisingly mature early galaxies aren't as surprising if dark matter behaved differently than we think in the early universe. Some scientists have proposed that dark matter might not be uniformly distributed, or that it might interact with itself in subtle ways we haven't detected. If true, these factors could change our understanding of structure formation without requiring the universe to be older or younger than currently thought. Then there's dark energy, which is even more mysterious. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. That's right, not only is the universe expanding, but the expansion is getting faster. This was discovered in the late 1990s by observing distant supernovae, and it was such a surprise that the discoverers won the Nobel Prize. Dark energy makes up about 68% of the universe, and we have no idea what it is. The leading explanation is that it's a property of space itself, something Einstein called the cosmological constant. But it could also be a dynamic field that changes over time, or something else entirely that we haven't even thought of yet. Why does dark energy matter for cosmic age? Because it affects the expansion rate of the universe. If dark energy has been constant throughout cosmic history, then our calculations are probably correct. But what if dark energy has changed over time? What if it was weaker in the past and stronger now, or vice versa? Such changes would alter the expansion history of the universe, and that would change our age calculations. Some scientists have proposed variations of dark energy called quintessence or phantom energy, which change their strength over time. If something like this is real, it could help explain the Hubble tension we talked about earlier. Maybe the early universe was expanding at one rate, and the local universe is expanding at a different rate, not because of measurement errors, but because dark energy has evolved. Here's another intriguing possibility. What if our understanding of gravity itself needs revision on cosmic scales? This is controversial, and most scientists think our current theory, general relativity, is correct. But there are alternative theories of gravity that predict slightly different behavior for the expansion of the universe. If one of these alternatives were correct, it could change our age estimates. The point I'm making is that there's a lot we don't know. Dark matter and dark energy together make up the vast majority of the universe, and we're still figuring out what they are and how they behave. Any discoveries or revisions in our understanding of these components could have implications for the age of the universe. This uncertainty isn't a weakness of science, it's actually a strength. Science progresses by identifying what we don't know and working to fill in those gaps. The fact that we can acknowledge the limits of our knowledge while still making progress is what makes the scientific method so powerful. We don't have to have all the answers to make meaningful progress, but it does mean we should hold our conclusions tentatively. That 13.8 billion year age isn't carved in stone. It's our best current estimate based on available evidence and our current understanding of physics. As our understanding improves, the number might change, and that's okay. In fact, that's how science is supposed to work. Alternative theories and speculative ideas. Now let's venture into slightly more speculative territory. While the mainstream scientific community continues to refine measurements within the standard Big Bang model, some researchers have proposed more radical alternatives. These ideas are definitely outside the mainstream, and most scientists are skeptical of them, but they're worth discussing because they show the range of possibilities being considered. One alternative that occasionally surfaces is the idea of a cyclic or bouncing universe. Instead of the Big Bang being a true beginning, what if it was a transition from a previous phase of the universe? In some cyclic models, the universe goes through repeated cycles of expansion and contraction. Each cycle ends in a big crunch, where everything collapses back together, followed by a new Big Bang that starts the next cycle. If something like this were true, the age question becomes more complicated. Is the universe 13.8 billion years old, or is it infinitely old, with our current cycle being just the latest in an eternal series? Some versions of these models propose that each cycle lasts trillions of years, meaning the current cycle could be much older than 13.8 billion years, even if the most recent bang was that long ago. The evidence for cyclic models is slim, and they face significant theoretical challenges. But they illustrate an important point. The Big Bang might not have been the absolute beginning of time and space. It might have been a transition, a phase change in something that already existed. Another speculative idea involves the possibility of varying constants of nature. In physics, we have fundamental constants like the speed of light, the gravitational constant, and the fine structure constant. These numbers are, well, constant. They don't change. At least that's what we've always assumed. But what if they're not perfectly constant? What if they vary very slowly over cosmic time, or differ in different regions of space? If the speed of light was different in the early universe, or if gravity was slightly stronger or weaker, it would affect everything, from the expansion rate to the formation of stars and galaxies. Our age calculations assume these constants are truly constant, so any variation would introduce errors. Scientists have searched for evidence of varying constants by looking at light from distant quasars and studying the CMB. So far, they haven't found any convincing evidence of variation, but they also can't rule it out at very small levels. If future observations detect variations, it would revolutionize physics and could change our understanding of cosmic age. Then there's the simulation hypothesis, the idea that our universe might be a computer simulation created by some advanced civilization. This is more philosophy than science, and there's no way to test it, but it's fun to think about. If the universe were a simulation, concepts like age become ambiguous. How old is a simulated world? Is it as old as its simulated history suggests, or only as old as the simulation has been running? I mention this not because I think it's likely, but because it highlights how our concept of time and age depends on our assumptions about the nature of reality. If those assumptions are wrong, our age calculations might be meaningless or need complete reinterpretation. More seriously, some scientists have suggested that the universe might have gone through a phase of slow expansion before the hot Big Bang we know about. This is called the slow roll period in some models of inflation. If such a phase existed and lasted longer than we think, the universe could be older than our measurements suggest, without contradicting any observations. There's also ongoing research into the very beginning of the universe, that first fraction of a second. Quantum mechanics tells us that time itself becomes fuzzy and undefined at extremely small scales. Maybe the question, how long ago did the Big Bang happen, doesn't even have a precise answer, because time itself was uncertain in that earliest moment. These are all highly speculative ideas, and I want to emphasize that they're not accepted by the mainstream scientific community. The standard Big Bang model, with an age of about 13.8 billion years, remains the best explanation for the evidence we have. But science progresses by exploring alternatives, testing them against observations, and seeing which ones survive. Sometimes the alternatives fail, and we confirm the standard model. Sometimes they succeed, and we learn something new. The key is to remain open-minded while also being rigorous. Extraordinary claims require extraordinary evidence, as the saying goes, Until there's compelling evidence for these alternative ideas, they remain interesting possibilities rather than established facts. What new observations tell us? Let's come back to firmer ground and talk about what recent observations are actually telling us. Beyond the James Webb Space Telescope findings and the Hubble tension, there have been several other observations that are making scientists reconsider various aspects of our cosmic timeline. One interesting development comes from observations of globular clusters. These are ancient, tightly packed groups of stars that orbit galaxies. Many globular clusters are extremely old, possibly among the first structures to form after the Big Bang. By studying them, astronomers can get clues about the early universe. Recent measurements have refined the ages of some of these globular clusters, and the results are intriguing. Some appear to be about 12 to 13 billion years old, which fits comfortably within the 13.8 billion year age of the universe. But the uncertainty in these measurements is fairly large, and there's always the possibility that some clusters are older than we think. What makes globular clusters particularly interesting is that they exist in different environments. Some orbit our own Milky Way galaxy, while others are found in distant galaxies. By comparing the ages of globular clusters in different locations, scientists can test whether stellar evolution works the same way everywhere, and whether our age dating methods are consistent. Another line of evidence comes from the large-scale structure of the universe. Galaxies aren't randomly scattered through space. They're organized into enormous structures: walls, filaments, and voids. These structures formed as matter clumped together under gravity over billions of years. The size and distribution of these structures depend on how long they've had to grow. If the universe is older, structures should be larger and more evolved. If it's younger, they should be smaller and less developed. Current observations of large-scale structure are generally consistent with the 13.8 billion year age, but there's some wiggle room in the interpretation. One particular puzzle involves what astronomers call the cosmic web, the network of filaments connecting galaxy clusters. Some of the largest structures in this web seem almost too big for their age. They're on the edge of what should be possible, given the time available since the Big Bang. This could be a statistical fluke, or it could be a hint that structures had more time to grow than we think. There's also intriguing evidence from studies of very distant quasars. Quasars are incredibly bright objects, powered by supermassive black holes at the centers of galaxies. Some quasars exist in the early universe, less than 1 billion years after the Big Bang. The problem is that the black holes powering them are already supermassive, containing millions or even billions of times the mass of the Sun. How did these black holes grow so large so quickly? Black holes grow by consuming matter, but there's a limit to how fast they can do this, set by the physics of how matter falls into them. To reach the masses we observe, these black holes either needed to start out much larger than we'd expect, or they needed more time to grow. Once again, we see a potential tension between observations and our timeline. Scientists are exploring various solutions to the quasar problem. Maybe black holes form directly from collapsing gas clouds in the early universe, rather than from the death of stars giving them a head start. Maybe they grew through mergers with other black holes, which can be faster than gradually consuming gas. Or maybe, once again, the universe is older than we think, giving these black holes more time to grow. What's particularly interesting is that many of these puzzles point in the same direction. The mature early galaxies, the ancient stars, the large cosmic structures, the supermassive black holes, they all suggest that things happened faster in the early universe than our models predict. And one straightforward way to resolve all of these tensions is simply to give the universe more time. But before we jump to that conclusion, we need to consider other factors. Maybe structure formation was more efficient in the early universe than we realize. Maybe the initial conditions set by inflation were different than we think. Maybe there are processes we don't understand that sped things up without requiring more time. This is where the scientific method really shines. When multiple independent lines of evidence point toward the same conclusion, scientists take notice. But they also look for alternative explanations and test them rigorously. The goal isn't to prove a preferred theory right, it's to figure out what's actually true, regardless of what we expected or wanted to find. Recent observations from ground-based telescopes have also contributed to this discussion. Large surveys like the Sloan Digital Sky Survey and the Dark Energy Survey have mapped millions of galaxies, giving us unprecedented statistical power to study the universe's evolution. These surveys have revealed subtle patterns in how galaxies are distributed and how they've changed over time. Some of these patterns suggest that the matter content of the universe might be slightly different than the Planck satellite measurements indicated. If true, this would affect the expansion history and the age calculation. Other patterns hint at complexities in how dark energy behaves, which could also change our timeline. The point is that observational cosmology is in a fascinating place right now. We have incredibly precise measurements from multiple sources, and they're starting to reveal tensions and inconsistencies. These aren't necessarily signs that our theories are wrong. Often they're signs that we're at the frontier of knowledge, where the next big discoveries happen. How scientific consensus changes. This brings up an important question about how science works. How does the scientific community actually change its mind when confronted with new evidence? Because if the universe really is older or younger than we think, accepting that would require revising one of the most fundamental numbers in cosmology. That's not something that happens quickly or easily. The process starts with individual observations and measurements. A telescope finds something unexpected. A research team publishes their findings in a scientific journal, where other experts review the work before publication to check for errors and make sure the methods are sound. This is called peer review, and it's the first filter that new ideas have to pass through. But peer review isn't the end of the process. Once a paper is published, the broader scientific community examines it. Other researchers try to replicate the findings using their own instruments and methods. They look for alternative explanations. They check whether the result is consistent with other observations. This process can take years. Initially, when JWST found those surprisingly mature early galaxies, there was a lot of excitement and some dramatic headlines suggesting we might need to throw out the Big Bang theory entirely. But as scientists dug deeper, the picture became more nuanced. Some of the early mass estimates were probably too high. Some of the objects might not be what they first appeared to be. The observations are real and important, but they don't necessarily overturn everything we know. This is normal in science. First observations are often rough around the edges. As more data comes in and analysis improves, the picture becomes clearer. Sometimes the initial surprising result stands up to scrutiny and becomes accepted. Sometimes it fades away as errors are found or better explanations emerge. For a major revision, like changing the age of the universe, to gain acceptance, several things would need to happen. First, the evidence would need to be overwhelming. We're not talking about one or two puzzling observations, but a consistent pattern across multiple independent measurements. Second, there would need to be a coherent alternative model that explains all the observations better than the current model does. And third, that alternative model would need to make testable predictions that could be verified. We're not there yet with the age question. The evidence is intriguing and the tensions are real, but they're not yet overwhelming. Scientists are still trying to reconcile the observations within the standard framework before jumping to more radical conclusions. That's not close-mindedness, it's intellectual caution, the recognition that extraordinary claims require extraordinary evidence, but the process is ongoing. New telescopes are being built and launched. More precise measurements are being made. Theoretical models are being refined. If the universe really is older or younger than 13.8 billion years, the evidence will eventually become undeniable, and the scientific consensus will shift. History gives us examples of how this has happened before. In the early 20th century, most scientists believed the universe was eternal and unchanging. The idea of a Big Bang was radical and controversial, but as evidence accumulated from Hubble's observations of galactic redshifts to the discovery of the cosmic microwave background, the consensus shifted. Today, the Big Bang theory is accepted by virtually all cosmologists. Similarly, the age of the universe itself has been revised multiple times. In the 1950s and 60s, estimates range from 2 billion to 20 billion years. As measurements improved, the range narrowed. By the 1990s, it had converged to somewhere between 10 and 15 billion years. The Planck satellite refined it further to 13.8 billion years. Each refinement was based on better observations and better understanding of the physics involved. Could we be on the verge of another refinement? It's possible. The Hubble tension and the JWST observations might be telling us that 13.8 billion years needs adjustment. Or they might be revealing something else entirely about the universe that doesn't change the age, but changes how we understand its evolution. Time and more observations will tell. The role of technology in cosmic discovery. It's worth taking a moment to appreciate just how far our technology has come. A century ago, we didn't even know other galaxies existed. Edwin Hubble's discovery that the Andromeda Nebula was actually a separate galaxy outside our own Milky Way only happened in the 1920s. Before that, many scientists thought the entire universe was just our galaxy and nothing more. Today we can detect galaxies billions of light years away. We can measure the temperature of the cosmic microwave background to millionths of a degree. We can observe the universe as it was when it was less than 400 million years old. This is an incredible achievement, made possible by advances in telescope technology, detector sensitivity, and data analysis techniques. The James Webb Space Telescope represents a quantum leap in our observational capabilities. Its mirror is about 6.5 meters in diameter, much larger than Hubble's 2.4-meter mirror. More importantly, it observes in infrared wavelengths, which allows it to see through cosmic dust and detect the light from very distant, ancient objects that has been redshifted into the infrared by the expansion of the universe. JWST's sensitivity is so high that it can detect the heat signature of a bumblebee at the distance of the moon. When pointed at the early universe, it can see galaxies that formed when the cosmos was just a few percent of its current age. This capability is unprecedented, and it's why JWST is revealing things we've never seen before. But JWST is just one instrument. Ground-based telescopes are also getting more powerful. The extremely large telescope being built in Chile will have a mirror 39 meters across when it's completed. The Large Synoptic Survey Telescope, now called the Vera C. Rubin Observatory, will repeatedly scan the entire visible sky, creating a movie of the changing universe and detecting billions of objects. On the theoretical side, computer simulations are becoming more sophisticated. Scientists can now simulate the evolution of the entire universe from shortly after the Big Bang to the present day, tracking billions of particles as they interact through gravity and other forces. These simulations help us understand what we should expect to see and allow us to test different theoretical models against observations. The combination of better observations and better theory is powerful. When they agree, we gain confidence in our understanding. When they disagree, we know there's something interesting to investigate. The current tensions we've been discussing are examples of that disagreement, and they're driving a new generation of research. Looking ahead, there are several upcoming missions and projects that could help resolve the age question. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will conduct large-scale surveys of the universe and make precise measurements of dark energy. The Square Kilometre Array, a massive radio telescope network, will observe the universe in radio waves and could detect signals from the cosmic dark ages, the period before the first stars formed. Even more ambitious are proposed missions to study the CMB with even greater precision than Planck achieved. These could detect subtle features in the ancient light that would tell us more about the very early universe and the conditions that led to the Big Bang. All of these technological advances share a common goal: to push back the boundaries of what we can observe and measure. Every time we build a more powerful telescope or develop a more sensitive detector, we see things we couldn't see before. And often those new observations surprise us and challenge our understanding. That's not a bug in the scientific process, it's a feature, it's how we learn. What it would mean if we're wrong about the age. Let's do a thought experiment. Suppose future observations definitively show that the universe is actually 15 billion years old instead of 13.8 billion. Or maybe it's 12 billion years old. How significant would that be? Would it overturn all of cosmology, or would it be more like a correction to one number in a vast framework of knowledge? The answer is somewhere in between. The age of the universe is definitely an important number, but it's not the only important number. And changing it wouldn't necessarily invalidate everything else we know. Think of it like this: if you're building a house and you discover the foundation is a few inches off from where you thought, you don't have to tear down the whole house. But you might need to make some adjustments. Many of our cosmological observations and theories are independent of the exact age. We know the universe is expanding because we can see galaxies moving away from us. We know the Big Bang happened because we can see its afterglow in the cosmic microwave background. We know dark matter exists because we can see its gravitational effects. None of these fundamental discoveries would be invalidated if the age turned out to be different. What would change is our understanding of rates and timescales. How fast did the first galaxies form? How quickly did stars begin producing heavy elements? When did the first black holes appear? These questions depend on knowing the universe's age accurately, and revising the age would require revising our answers to these questions. It would also affect our understanding of cosmic expansion. If the universe is older than we think, but galaxies are as far apart as we observe, it means the expansion rate has been slower than we calculated. That would have implications for dark energy, that mysterious force accelerating the expansion. We'd need to revise our models of how dark energy has behaved over cosmic history. Conversely, if the universe is younger than we think, the expansion has been faster, and dark energy has been even more powerful than our current models suggest. Either scenario would tell us something new about the nature of dark energy and potentially about the fundamental physics governing the universe. There would also be philosophical implications. Humans have always been fascinated by questions of origins and endings. How old is the universe? How did it begin? How will it end? These questions touch on deep aspects of how we see ourselves and our place in the cosmos. If the universe is older than we thought, it means that the processes leading to our existence, the formation of galaxies, stars and planets, the emergence of life, the evolution of intelligence, all happened in a slightly different context. We'd have more time to fit into the cosmic story, which might affect how we think about the likelihood of life elsewhere in the universe. But let's be clear, we're probably not talking about a massive revision. Even if the age needs adjustment, it's likely to be by hundreds of millions of years, not by billions. The universe isn't going to suddenly be 50 billion years old or 5 billion years old. The basic framework would remain intact, with refinements rather than revolutionary changes. This is actually how science usually progresses. Revolutionary paradigm shifts, like the acceptance of the Big Bang theory itself, are rare. Most of the time, science advances through incremental improvements, small corrections, and gradual refinement of our understanding. It's less dramatic than a scientific revolution, but it's how we've built up the incredibly detailed picture of the universe we have today. The limits of human knowledge. As we near the end of our exploration, it's worth reflecting on the limits of what we can know. There are some aspects of the universe that might be fundamentally unknowable, at least with current physics and technology. For example, we can only see a finite portion of the universe, limited by the speed of light and the age of the universe. Light from regions more than about 46 billion light years away will never reach us because space between us and those regions is expanding too fast. This boundary is called the cosmic horizon, and it limits what we can observe. Could there be regions beyond our horizon where conditions are different? Where the laws of physics as we know them don't apply? Where the timeline of cosmic history played out differently? We can't know because we can't see there. Our measurements and theories are based on the observable universe, and we have to be humble about extrapolating beyond that. There are also theoretical limits to what we can know about the very earliest moments of the universe. Quantum mechanics tells us that at extremely small scales and high energies, the classical concepts of time and space break down. There's a limit called the Planck time, about 10 by 43 seconds, below which our current theories can't describe what happens. The Big Bang itself occurred at or before this Planck time, which means we may never be able to know exactly what happened at the moment of creation. We can study the universe from fractions of a second after the Big Bang onward, but that first instant might remain forever beyond our reach unless we develop a theory of quantum gravity that can describe it. This doesn't mean we should give up on trying to understand. It just means we should be aware of the boundaries of our knowledge and honest about what we do and don't know. Science has made incredible progress in pushing back those boundaries, revealing things our ancestors couldn't have imagined. There's no reason to think we've reached the end of what we can discover. But there's also beauty and mystery in acknowledging that the universe is bigger and more complex than we can fully comprehend. The fact that we can ask questions about the age of the universe, that we can devise experiments and observations to try to answer those questions, and that we can continue refining our understanding over time, that's itself remarkable. Human curiosity has driven us to build telescopes that can peer across billions of light years of space and billions of years of time. We've developed mathematical models that can describe the behavior of the entire cosmos. We've figured out ways to measure things that seem impossibly distant and impossibly small. And we've done all of this in just a few centuries of modern science. What will we know a century from now? What questions that puzzle us today will have clear answers? What new mysteries will we have uncovered? It's impossible to say, but if history is any guide, the future of cosmic discovery will be even more exciting than the present. Reconciling different lines of evidence. So where does all this leave us? We've talked about mature early galaxies, ancient stars, the Hubble tension, dark matter, and dark energy, and various other pieces of the cosmic puzzle. How do we put it all together? The honest answer is that we don't have a complete picture yet. Science is a process, not a destination, and we're still in the middle of figuring things out. But we can make some general observations about where the evidence is pointing. First, the standard model of cosmology, with a universe about 13.8 billion years old, still works remarkably well for most observations. It successfully predicts the cosmic microwave background, the abundance of light elements like hydrogen and helium, the large-scale structure of the universe, and many other phenomena. This is not a theory in crisis. It's a theory that's being tested and refined. Second, the tensions and anomalies we've discussed are real, not just measurement errors or flukes. Multiple independent research teams using different methods are finding similar results. The Hubble tension, in particular, has persisted and even grown more significant as measurements have improved. The early galaxies found by JWST continue to puzzle astronomers. These observations are telling us something, even if we're not sure yet what that something is. Third, there are multiple possible explanations for the observations, and we don't yet know which is correct. Maybe the universe is older than 13.8 billion years. Maybe it's younger. Maybe the age is right, but our understanding of how quickly structures form needs revision. Maybe dark energy behaves differently than we thought. Maybe there's something about the early universe we don't understand. The key is that scientists are actively working to distinguish between these possibilities. They're making new observations, running simulations, developing theoretical models, and testing predictions. This is the scientific method in action, the process of systematically narrowing down the possibilities until we converge on the truth. One promising approach is to look for observations that would clearly distinguish between different explanations. For example, if the universe is older, we should find even more ancient stars and even more mature early galaxies as we look deeper. If structure formation was just more efficient than we thought, we should be able to identify the physical processes that made it faster and verify that they work as predicted. Another approach is to improve our measurements of key parameters like the Hubble constant. If the tension between different measurement methods is real and not due to systematic errors, it should remain as measurements get more precise. If it's due to errors, it should go away as those errors are identified and corrected. Scientists are also working on better theoretical models. Can we develop a model of the early universe that naturally produces the observations we see without requiring the universe to be older or younger? Can we identify modifications to dark energy or dark matter that would resolve the tensions? The beauty of the scientific process is that it's self-correcting. If we're wrong about something, continued observations and experiments will eventually reveal it. The truth has a way of asserting itself as evidence accumulates. We might not know the answer today or even next year, but we're working toward it systematically. The human side of cosmic discovery. Before we wrap up, I want to touch on something that often gets overlooked in discussions of science: the human element. Behind every observation and every theory are real people, scientists who have dedicated their careers to understanding the universe. And the question of cosmic age isn't just an abstract academic exercise to them. It's personal. Imagine spending decades mastering the techniques to measure distances to galaxies or to analyze the cosmic microwave background. You've contributed to establishing what seemed like a solid, reliable number, 13.8 billion years, and then new observations come along that challenge that number. How do you react? Some scientists might feel defensive, reluctant to abandon something they helped establish. Others might be excited by the possibility of a major discovery and eager to explore new ideas. Most probably feel a mix of both. This is natural and human, and it's part of how science works. The important thing is that the scientific community has mechanisms to work through these human reactions and focus on the evidence. Peer review, replication of results, open publication of data. These processes help ensure that personal biases don't unduly influence the conclusions we reach. There's also something wonderfully humbling about all this. The universe doesn't care what we think or what we want to be true. It simply is what it is. Our job as humans is to observe it as carefully as we can, think about it as clearly as we can, and gradually build up a picture that matches reality. Sometimes that means admitting we were wrong, or that we don't know something we thought we knew. This humility is actually one of science's greatest strengths. Unlike dogmatic systems that claim to have all the answers, science is comfortable with uncertainty and willing to revise its conclusions when evidence demands it. The phrase "I don't know" or "we're not sure yet" isn't a weakness. It's an honest acknowledgement of the boundaries of current knowledge and an invitation to push those boundaries further. The scientists working on these questions about cosmic age are at the frontier of human knowledge. They're the explorers of our time, not venturing into unknown lands on Earth, but into unknown realms of space and time. They're asking and trying to answer some of the most profound questions humans have ever contemplated. How did everything begin? How old is the universe? How did we come to be? And here's something amazing. We live in a time when ordinary people can follow along with these discoveries. A century ago, cutting-edge physics was accessible only to a small elite. Today, anyone with internet access can read scientific papers, look at images from space telescopes, and learn about the latest discoveries. We're all invited to participate in the grand adventure of cosmic discovery, even if only as observers and students. What to watch for in the coming years? As we look to the future, there are several developments that could shed more light on the age question. Let me outline a few things to watch for in the coming years. First, continued observations from the James Webb Space Telescope. JWST has only been operating for a relatively short time, and it's expected to continue for many more years. As it observes more of the early universe and as scientists refine their analysis of what it's seeing, we'll get a clearer picture of those puzzling early galaxies. Are they really as massive and mature as initial estimates suggested, or will more detailed study reveal a different story? Second, new measurements of the Hubble constant. Several research teams are working on independent ways to measure this crucial parameter. The more methods we have, and the more they agree or disagree, the better we'll understand whether the Hubble tension is real and what it means. If all methods start converging on the same value, great. If they don't, that's telling us something important about the universe. Third, observations of the most distant objects we can detect. Astronomers are pushing to observe galaxies and quasars at higher and higher redshifts, meaning further and further back in cosmic time. Each new record-breaking discovery tells us something about how early structures formed and whether our timeline makes sense. Fourth, improved measurements of the cosmic microwave background. While the Planck satellite has already given us exquisitely precise measurements, there are always improvements to be made. Future experiments might detect subtle features in the CMB that current instruments miss, and these could provide new insights into the early universe. Fifth, advances in theoretical modelling and computer simulations. As computers get more powerful and our models get more sophisticated, we'll be able to simulate the universe's evolution in greater detail. This will help us understand what should be possible in the time available and whether our observations fit within theoretical bounds. Sixth, potential discoveries we can't even anticipate yet. History shows that some of the most important scientific breakthroughs come from unexpected observations, things we weren't specifically looking for. Who knows what surprises the universe has in store for us? In the shorter term, watch for scientific conferences and publications. When major results are announced at conferences like the American Astronomical Society meetings or published in journals like Nature and Science, that's where you'll hear about significant developments. Science journalism outlets do a good job of covering these announcements and putting them in context for general audiences. Also pay attention to how the scientific consensus evolves. Does the Hubble tension get resolved, or does it persist and intensify? Do more anomalies appear, or do existing ones get explained away? The trajectory over the next few years will tell us a lot about whether we're heading toward a major revision in our understanding or just fine-tuning what we already know. Conclusion: living with uncertainty. So after all this discussion, what's the answer? Is the universe older than we think? The honest answer is maybe. The evidence is intriguing, but not yet definitive. There are real tensions between different observations and measurements, suggesting that something in our understanding needs adjustment. That something could be the age of the universe, or it could be something else about how the universe evolved or how we measure cosmic distances and times. What we can say with confidence is that the universe is very old, certainly billions of years. The basic Big Bang picture, with a universe that was once extremely hot and dense and has been expanding and cooling ever since, is well established. The precise age, whether it's 12 billion or 13.8 billion or 15 billion years, is what's under discussion. And you know what? That's okay. In fact, it's exciting. It means we're at a moment in history where fundamental questions are still being actively investigated. We haven't figured everything out yet. There are still mysteries to solve, discoveries to make, frontiers to explore. The universe is under no obligation to make itself easy for us to understand. It's complex, vast, and full of surprises. Every time we think we have it figured out, it shows us something new that makes us question our assumptions. That's not frustrating. That's fascinating. As we continue to observe the cosmos with ever more powerful instruments, as we refine our theories and improve our measurements, we'll gradually converge on the truth. Maybe the universe is a bit older than 13.8 billion years. Maybe it's a bit younger. Maybe that number will stand the test of time. Whatever the answer turns out to be, we'll be one step closer to understanding the grand story of existence itself. The journey of cosmic discovery is far from over. We're not at the end of the story. We're not even at the middle. We're still in the opening chapters of humanity's attempt to understand the universe we inhabit. And that means the most exciting discoveries might still be ahead of us. What we do know is that the universe had a beginning. It has evolved over billions of years, and it has given rise to stars, planets, and ultimately, to us, beings capable of looking back across cosmic time and asking how it all began. That alone is pretty amazing when you think about it. So the next time you look up at the night sky, remember that you're looking back in time. The light from those stars left them years, decades, centuries, or even millions of years ago. The most distant objects visible to our telescopes show us the universe as it was billions of years ago, when it was young and galaxies were just beginning to form. By observing the past written in light, we're piecing together the story of cosmic history. And as that story continues to unfold, as new observations are made and analysed, we might indeed discover that the universe is older than we currently think, or we might confirm that 13.8 billion years is correct. Either way, we'll have learned something profound about the nature of reality. The question, how old is the universe, is one of the most fundamental we can ask. It connects to questions about origins, about time, about existence itself. The fact that we can ask it scientifically, that we can gather evidence and make measurements and test hypotheses, shows how far human knowledge has come, but it also reminds us of how much we still don't know. The universe contains mysteries we haven't even identified yet, questions we haven't thought to ask. Dark matter and dark energy, which make up 95% of the universe, remain mysterious. The nature of time itself at the quantum level is still debated. The ultimate fate of the cosmos is uncertain. These unknowns aren't failures of science. They're invitations to discovery. They're the frontiers where the next generation of scientists will make their mark, where the next great revelations await. And perhaps, just perhaps, hidden among these unknowns is the answer to whether the universe is indeed older than we currently think. For now, we watch, we measure, we calculate, and we wonder. We build better telescopes, develop more sophisticated theories, and gradually push back the boundaries of ignorance. It's slow work, requiring patience, careful thought, and intellectual humility. but it's also some of the most meaningful work humans have ever done. Because when we look up at the stars and ask, how old and how did this all begin, we're not just satisfying idle curiosity, we're fulfilling a deep human need to understand our place in the cosmos, to comprehend the context of our existence. We're writing the story of creation, not in mythology or metaphor, but in testable, verifiable science. And that story, however it ultimately unfolds, whether the universe is 13.8 billion years old or somewhat more or less, is magnificent. It's a story of cosmic evolution on an almost incomprehensible scale, of matter and energy organizing themselves into structures of increasing complexity, eventually leading to stars that forge heavy elements, planets where those elements combine into molecules, and finally, life and consciousness. We are, quite literally, the universe becoming aware of itself. We're made of atoms forged in the hearts of ancient stars. We're standing on a planet that's travelled billions of years through space, and we're using our minds, themselves the product of billions of years of evolution, to peer back across time and space to understand our cosmic origins. So is the universe older than we think? Maybe, probably not by much if it is, but the question itself and our ability to investigate it scientifically is a testament to human curiosity and ingenuity. As we continue that investigation, using new telescopes and new techniques, we'll refine our understanding, we'll get closer to the truth, and whatever that truth turns out to be, it will be fascinating, because the universe always is. Thank you for joining me on this exploration tonight. Keep looking up, keep asking questions, and keep wondering. The universe has many more secrets to reveal, and we're privileged to be living in a time when we can actually investigate them scientifically. Until next time, clear skies and curious minds.